Let's take another look at UV-Vis spectroscopy. And so we're not going to pull a lot of information from this. It's not nearly as useful as IR, NMR, mass spec, that kind of thing. It just tells you about the kind of conjugation properties of the compounds. And so for historical reasons, they're read a little bit differently. Remember when we were taking a look at IR, the y-axis was transmittance. Here it's absorbance. So instead of transmittance, we look at absorbance. And they're not directly related, or they're not super easily related to one another, right? If the transmittance is 50%, the absorbance is not 50 or something like that. And that's because there's a logarithmic function between the two. And so absorbance A is equal to the log of the incident radiation over the transmitted radiation. And so this I naught is the incidence light intensity. So how bright is the light that you're shooting at it, divided by the transmitted light intensity. And so if you transmit very little light, this will be a very tiny number, and it's in the denominator, which will make this overall a very big number. And then you take the log of it, which will then give you the absorbance. The main piece of information that we want to pull from this is the lambda max. The lambda max is the wavelength where the maximum absorption occurs. And in the case of UV-Vis spectroscopy, what we're talking about here is in terms of wavelength in nanometers, right? So we're talking about wave number when we're talking about IR. Here we're talking about wavelength. And so you can see almost every compound will have a lambda max. That's where it's absorbing the maximum amount of light. So this one's around, I don't know, something like 210 nanometers. And of course, remember what we learned, the more conjugated you get, the smaller this energy gap gets. So for example, if we take a look at butadiene, this absorbs at 217 nanometers. And then we take a look at hexatriene. Now we've got more conjugation, so this energy gap is smaller. But remember that when it comes to wavelength, a bigger wavelength is smaller energy. And so this goes to 258 nanometers, right? It's a bigger wavelength, smaller energy gap. And then if you keep adding more and more conjugation, you'll shift it to a higher and higher wavelength that it is absorbing. And again, there's all kinds of cool things you can do with these conjugated organic compounds in terms of modulating their color. So one of the most popular example is your organic light emitting diode, OLEDs, right? So maybe you have an OLED TV, or there's a lot of promise since organic compounds are kind of plasticky, they're stretchable, they're flexible to make flexible TVs or wearable electronics. And so this works on the same principle of the stuff that we've been learning here. And so if you take a look at this little diagram, what you have here is this light emissive polymer, right? The light emissive polymer, that's going to be your conjugated polymer. And so it's going to have this pi to pi star gap in it, except in OLEDs, instead of it absorbing light, what we do is we inject electron in this higher energy state, let it relax down, and then when it does so, it emits a light. And the frequency or the color of this light is going to be proportional to this pi star gap, which is in turn controlled by the amount of conjugation, or you can even use electron donating or withdrawing groups. And so you can see how you can go from the structure of the compound to different properties, such as the light emitting in an OLED.